For this week's video, we're going to be talking about chapter 4 in our textbook on decrease and conquer. So last chapter was on brute force. So we just hit something with a hammer until it dies. We're trying to get a little smarter this time, right? We're trying to come up with algorithms that are a little bit more efficient, okay? A little bit more clever in some ways, okay? So with this, we're going to call this whole idea is that we're going to do an incremental approach, right? We're going to solve a smaller version of the problem than the original and then try to put those solutions together, okay? And there really are three major categories or major variations of this. We can do a decrease by constant, okay? That's usually decreasing by one at a time, and that's just brute force, just another name for brute force, okay? We can do a decrease by a constant factor, which is usually the constant factor's 2. So we're decreasing it in half every time, which next chapter we're going to talk about divide and conquer, and that's usually what we mean there, okay? And then finally, there are some cases where we have a variable size decrease, okay? So in the book, gives some examples of the three of these. Again, the first one's just the brute force, nothing really new there, and it gives some examples of how we could do that, okay? Then we have the decrease by a constant factor, okay, where you're starting with a problem of size n, you're dividing that problem in half to size n divided by 2, then you get a solution to the subproblem, which gives you a solution to the bigger problem, okay? And that's really the issue there. And then finally, with the variable size decrease, it's going to be something like we've done this example before, I think. We're doing the GCD, okay? This is Euclid's algorithm for this. The GCD of m and m is equal to the GCD of m and m mod n, okay? And then you just keep replacing those numbers. So that one, there's not a constant amount that it produces it by. It just depends on the way the arithmetic ends up going, okay? So that's an example of a variable one, okay? So when we're talking about this decrease by one technique, something that we can do is a different sort. We'll be talking about lots of sorts in this book. We're still not super efficient, but this one's a little bit better. This one's called an insertion sort, okay? So the idea here is that if we sort a smaller array, then it's probably easier, okay? So we're gonna break up our bigger array into a smaller bit and kind of go from there, okay? So this is the idea here. Here's our algorithm on page 134, okay? And with this, the key is that in this outer loop here, we're starting off and we're picking how much of the loop or how much of the array we're going to sort, okay? And then we're basing our J based on this I that we're picking. And then we're going to go through the loop and sort from there, okay? As an example, and you should look at this more clearly, obviously, as an example of how this works, here are some sample numbers, okay? And in the original order, we start at this first time by making the assumption that if we're only dealing with one element of the array, then that element is sorted, okay? So the next idea where the name comes from is we're going to insert the 45 into the right position, okay? So we do that by putting it in the first position. We can now move this vertical bar, which means we're showing that the first two numbers are sorted, okay? We then look at 68, put it in the right spot, 90, put it in the right spot, and so forth until we are done, okay? So that's the idea, okay? So the basic operation here, okay, again, looking back at the algorithm, is going to be the comparison here, the comparison where we're seeing if the AJ is greater than V, okay, the second part of this one, okay? Okay, so we're looking at that one rather than this one, again, for reasons like in the homework we talked about before to make sure we're counting them all, okay? And since there are two loops in essence, we can figure, and it turns out we're correct, that this is going to be the big theta of n squared, okay? And we show this by doing the summation here. We work all this out, and that's what we get, okay? Again, we're looking at the highest power of n. We're not looking at the actual, 2n squared or whatever it happens to be, okay? We're looking for the highest power of n only, okay? So that's what that looks like, okay? So that's the first section, okay? There's another one we'll talk about later that actually it's in the problems, a shell sort. Not sure we're gonna work on a shell sort or not. Just a different way to do a sort. But the insertion sort is gonna be enough for us, okay? Homework problems I will work on later. Okay, and then yeah, problem 12, it talks about how a shell sort is different. Okay, so section 4.2 talks about this concept. Sorry, that's it, of topological sorting. Okay, so with the topological sorting, it's a problem that we deal with directed graphs. So remember, a directed graph is a graph where there's not just an edge between 2 points. There are 2 possible edges. And they're directional. Okay, so you can go from A to B, but maybe not go from B to A, or maybe you can do both. Okay, so when you have these directions with the arrows, you have a directed graph or a digraph. Okay, so we often do this. We see this problem if you're looking at things that have to happen before other things happen. So the example we're going to do in a minute is using prerequisite courses. Okay, and how you can figure out the correct path to take through them. Okay. So in this case, we have on the page here in figure 4.5, a directed graph. I can get from A to B, B to A, different lines. I can get from A to C, but not C to A. Okay, and you have to look at those things. And then we get the depth first and breadth first are still the way we would go. Okay, so with the depth first, you're trying to get away from your starting point as quickly as you can. With the breadth first, you're going to move at all of the processes that are connected to the current one that you're on, okay? And we get our depth first forest there, which looks a little bit different because of this idea of the directed graph, okay? And then we talk about a directed cycle, which is basically the cycle in a graph means that there's a circle somewhere, okay? And then if you have a DFS forest, the depth first search forest of a digraph with no back edges at all, then you don't have a cycle, okay? And we call that a DAG or a directed acyclic graph, which will probably come up again later, okay? So we're going to look at this next example. So this is right here on page 139. So it's our motivating example, as they say. Let's say that there are 5 required courses, okay, for whatever degree program we're talking about here. And we have a part-time student who wants to take these courses, okay? So they can be taken in any order, except we have these prerequisites. So C1 and C2 have no prerequisites. You can take them whenever you want. You can't take C3 until you've taken both C1 and C2. C4 requires C3, and C5 requires both C3 and C4, okay? You can only take 1 course per term. What's the best progression through that? Okay, so again, we're calling this kind of problem, topological sorting. Okay, so here's a digraph that represents this. Okay, that C1 and C2 have no prerequisites. C3 requires both of those. C4 requires C3. C5 requires both C3 and C4. Okay, so that's what we get there. Okay, so that's the digraph there. Okay. In problem B here, we're looking at the depth first traversal stack. Okay, and then we have the popping off order there, the stuff we've done before. Okay, so this idea of topological sorting, then a couple of ways to do it. Okay, so the first way, okay, we're going to it's based on a depth first search. Okay, so we're going to do this depth first traversal. We're going to note the order in which the vertices become dead ends. Okay, so they're popped off the traversal stack. Okay, so where do you stop at? Okay, if you reverse this order, then it's going to yield the topological sorting problem. Okay, so in this case, if we start with C1 or C2, it doesn't matter. Okay, no, that's the wrong one. That's the next problem. Here we go. Yeah, they're showing that here. So the first one here, okay, whichever one you start with, where you end up and you can't go any further is the C5. Okay, that's the dead end. Okay, if you remove C5, the next dead end is going to be C4. Okay. If you remove C4 and C5, then whichever one you start with, you end at C3. That's your next one. And then C1 and C2 don't matter. They're going to go either way. Okay. So again, looking at it this way, so C1 or C2 is your first course, followed by C3, C4, and C5. Okay. And that gives us here our topologically sorted list. Okay. So then the other way is to look at the sources. Okay. It's where we're starting from. Okay. And that means, so again, I didn't define enough. In our example with the first way of doing it, the depth first, we're looking for a vertex that has no outgoing lines. Okay, that's when we know we're done. Okay, we're assuming this is an acyclic graph, so we're not going to go around in circles. Okay, so in this case, we're looking for sources, which means they have no incoming arrows, only outgoing. Okay, so in this case, we see that of course C1 or C2 are both going to be either one's will start. Okay, but we're going to say we're going to delete C1. Okay, then we're going to delete C2. Okay, so those are in a forward order. Okay, C3 is the one that's left as the source, and then C4, and then C5. Okay, and we're going to get the same order either way. Just sometimes it's easier than other times. Okay, so the homework's going to have you do these kinds of things. Okay, and again, if you find a cycle, then you can't do the problem. Okay. We next have some examples for generating combinatorial objects. Okay, so this is the first one. For example, we're going to do with some permutations here. Okay, we've seen this kind of problem before. So they start off doing a problem here. For example, we're going to insert 2. So we're going to insert 2 into the 1 to the right and to the left. We're then going to insert 3 both ways. Okay, and then we're going to insert 3 and 2, 1 both ways just to generate. Okay, so this gets us to a little more generally useful algorithm called Johnson-Trotter. Okay, presumably 1 or 2 people named Johnson and Trotter, or Johnson-Trotter combined, came up with this idea. Okay, with this one, you're going to put in all of the numbers that you want to have a permutation of. Okay, so, and we're assuming that these are in some kind of an order. Okay, we're going to start with all these little arrows here. Okay, and here's the idea here. While the last permutation, so we're going to while the last permutation has some mobile element, okay, which means it has not moved all the way over yet, we're going to find its largest mobile element. We're going to swap k with the adjacent element that k's arrow points to. We're then going to reverse direction of all the elements that are larger than k and add the new permutation to the list. Okay, so here's the example if n is equal to 3. Okay, so we have 1, 2, and 3. Okay, so in this case, the 3 is the largest mobile element. Okay, so we're going to move it in the direction that the arrow says. So that's 1 to the left, gives us to here. Okay, so once we're at this point, okay, we now have, so we've gone from 1, 2, 3 to 1, 3, 2. Okay, we still have one more to make in that the 3 is still the biggest. It's still pointing left. We're going to go left with 3 and move it all the way over to the 3, 1, 2. Okay, now that we've moved 3 all the way over, we're reversing the arrow at the top. It's a little bit hard to see, but that's what's happening there. Okay, we then have the 1 and the 2. Okay, we now move the 3 back over in the direction it's going. Okay, to give us 2, 3, 1. Okay, and note the direction of the arrows there. Okay, and then finally we get to 2, 1, 3 as the 3 completes its way going back and forth. Okay, so in this way we're kind of switching around the orders as we go. Okay, so you can do that with more than 3, certainly. Okay, so there's another algorithm here for a lexicographical permute. In this case, we're wanting it to be so they remain in alphabetical order, basically, as they're being permuted. Okay, which the other one did not. So that's something that you can work through as well. Okay. We then have an algorithm for generating subsets called the power set. Okay. And the way we do this, here's an example. Here's the bottom up way. We start with the empty set, okay, which has 0 elements. We then go with the set of 1, okay, which has the empty set and just the set of 1. It's the subsets we can generate. If we have, when n goes to 2, we're adding in A1 and A2, and then A1 and A2 together. That's a proper subset. And then finally, we have A1, A2. The A1, A2 is still there. We're going to add A3 as its own set, and then A1, A3, and then A2, A3, and then A1, A2, A3. Okay. So that can get a little hairy with bigger numbers. Okay. So one way we can help with that, okay, is to do some coding like we talked about before, okay, where we're going to put a 0 if the current, if that number of the element is in the set, if it's not, sorry, and a 1 if it is, okay. So we can do that then through this thing here, okay. Well, here's where they're doing those strings to show, for example, 0, 0, 1 is going to be just a 1 in the third position, so A3 is in the set, and 0, 1, 0, and so forth, okay. And what we're doing here basically is we're just counting, right? This is binary counting, so it's 0, 1, 2, 3, 4, 5, 6, 7. So those are the different ways to permutate this particular set, okay. But the question is, and I got ahead of myself here, the question is, if you want to find a way to go through where we're only doing 1 bit change per jump, okay? So for example, in this case, from 001 to 010, both the second and third bits both switch, okay? So a way to do this is called the binary reflected gray code. So if we look here, we go 001, 0, 000, 001, only one change. 010, only the middle one changes it. 010, only this one changed. 110, 111, 101, and 100. Okay. So again, this is going to minimize the only 1 bit changes per time through. Okay. And here's an algorithm of how we can use that. Okay. It's more exercise. I'll probably post exercises tomorrow, would be my guess. Then we get to the decrease by a constant factor, which we're just going to call divide and conquer, starting from here. And I think we've mentioned this problem before. It's the one of a binary search. Is if you have an array that's sorted, okay, then you know you can go into the middle and check to see if the key term that you're searching for is in the middle. So in this case, we're taking A to M to refer to our median point, okay? And we're going to check to see if A to M is equal to K, our search term, okay? If it's less than our search term, okay, we know that it must be in this A to 0, A to M minus 1 range. If it's greater than, then we know it must be in this part, okay? I think that I said that exactly the wrong way around, but you get the idea. If we're looking for 10 and this is 20, okay, we know it's got to be this left side. If we're looking for 10 and this is 5, we know it's got to be to that side, okay? So give an example here. So in this case, we've got this row of numbers and we're searching for 70, okay? Our middle is here at this 55, okay? And from this middle, okay, so just to see where we're at, to see what these little marks do for us, our L is at 0, our R is at 12, because the whole thing is in play, okay? So the median then becomes 6, okay? So at this median, we look to see, and we see that our answer is bigger than that, okay? So it can't be to the left, it's got to be to the right. So we're going to start at M plus 1, as we did up here, for our left one, and the right stays the same. Go in the middle there, okay? And then you can just concatenate if there's a tie or whatever you want to do, okay? And this M is 81, okay? 81 is bigger than what we're looking at, so we know we want to do the left half. So we move 1, this M minus 1, and the L stays the same. The R becomes into there, and we can go through that, okay? And we're eventually going to get, in fact, we may be there. Yes, L and M are the same. They point to 70. So we found it. Okay. So that's the idea of a binary search. Okay. And it's important that you understand what these L's and M's look like and what's happening with them. And if you have questions, let me know. We can go a little bit more. Okay. And here's the actual algorithm, the pseudocode to implement that. Okay. And then it talks about the efficiency of that. And again, we're not going to really, you should know the efficiency, but the calculating is not something we're going to worry about. Okay. This one certainly can have a best or a worst case scenario. You can find it immediately. The best case, just have to do it one time. Then the worst case we're looking at looks like that log 2 of n is going to be our average case. Okay. So this average case that's pretty good time. Okay, the log 2 of n basically means we're cutting things in half every time, which is good. Okay, there are better ways, but that's not a bad one at all. We have here another version of the fake coin problem here. Okay, so in this particular problem, though, that we know whether or not the fake coin is lighter or heavier. Okay, so you've got 12 coins and you know that the fake one's heavier. Okay, and this problem basically involves dividing the coins in half and weighing them against each other. And whichever one, since we know the fake coin's heavier, then the heavier pile must contain the fake coin. We have to keep weighing that. So we're able to get rid of half the coins at every point. Okay. And again, if you have an odd number of coins, so let's say you end up with 11 coins, what do? Well, you weigh 10 against 10. If they weigh the same, then you know you must have the fake coin in your hand. Okay. They don't weigh the same, then you know you don't have the fake coin in your hand, and you'll be able to tell which of the two is heavier. Okay. Lots of fake coins in this class. Okay. Another example here is a kind of an odd thing. It's a non-orthodox way of multiplying two positive integers called Russian peasant multiplication for some historic reason that I'm not aware of. So with this one, if we want to take n times m, if it's even, we take n times m is equal to n divided by 2 times 2m for whatever reason. If it's odd, then we're just going to have it be n minus 1 over 2 times 2m plus m. This apparently works out somehow, which is quite strange. Okay, but it just shows it's a way to do less work than you would normally have to do. So there's an example of that. Okay. Then there's a fairly macabre example here from ancient Israel, and this is the Josephus problem. Josephus was a Jewish historian. If you have read about, is it Masada, I think it's called, where they were, does it say it there? Oh, they're saying some city. I always heard it's Masada. Anyway, that they were at a fortress, and there were 40 of them, and they were in a cave, and they voted to die rather than surrender. So the way that Josephus came up with in order to do this was that every person should kill their neighbor. You know, they didn't have guns, so I guess they stabbed him or hit him with a stick or some such thing. So the first time around, you know, person number 1 kills person number 2, person number 3 kills person number 4, and so forth until there's no one left. Okay, the last person then has, I guess, has to kill themselves. I don't know. So Josephus figured out how to work it so he would be one of the last 2 left. And when he did, instead of killing the last person, he convinced them to surrender to the Romans. But anyway, so the problem here is to determine who the survivor is for a certain number of positions. Okay, so for example, pretty clear, the J of 2. If there are 2 people, then person 1 kills person 2, so the J of 2 is 1. Okay. If there are 3 people, okay, person 1 kills person 2. Okay. Person 3 kills person 1. So person 3, the J of 3 then is 3. Okay. And we can look at those different numbers. They give us here that if there are 6 people, okay, then 2, 4, and 6 get eliminated the first pass through the circle. And then the people in 3 and 1 get eliminated the second time through. So the winning position there, the survivor, would be 5. So the J6 is 5. Okay. And then we see the J of 7 is 7. And it just shows how we do these. Okay. So we're going to talk about even and odd cases here differently. Okay, so if we're any j to 2k, okay, we're going to get this formula here. It's 2 of jk minus 1. Now, if there's an odd case, if it's 2k plus 1, then we're going to go through and get this formula. Okay, so this is going to give us a solution on how to figure out those numbers going forward. Okay, and there's some more homework there. I'll pick some of these out for us. Okay. And then we have one with a variable size decrease. Okay, for this one, we talked about using Euclid's algorithm back in section 1.1, but that's a good example. But we're going to have a couple other examples of that. Okay, the first one here is computing the median. Okay, in the selection problem. So the selection problem, we're going to find the kth smallest element in a list of n numbers. So not the absolute smallest, but the kth, the number k if you put them in an ordered list. Okay, this number is called the kth order statistic. So if k is equal to 1 or k equal n, then we're just looking at, we want the smallest number as k equal 1. If k is n, we're talking about the biggest number. Okay, so there are other things we can do here to try to figure this out. Okay, so it says here, a more interesting case, if we're looking at the k is equal to the ceiling of n divided by 2. That's, you want to find the element that's not larger than 1/2 and not smaller than the other half. So we're going to call this the median, right? So if there are 10 items, then we're going to want the 5th order statistic, right in the middle. Okay, so one way you can do this is sort the whole algorithm and find out where it's at. Okay, but that's kind of overkill because it doesn't ask us to sort. It only asks us, in essence, to partition this. Okay, this idea we're talking. We're going to partition the given list around some value. Okay, we don't care the order in each set. We just want to find what's in the middle. Okay, so for this, okay, the idea here, it's going to be a rearrangement of the list elements so that the left part contains all the elements smaller than or equal to p. P is our pivot point, and then the others that are bigger than that. Okay, so if we start by taking the first element of our list as p, then when we're done, we're going to move it. So we're going to have all that are less than or equal to p, followed by p, followed by all that are greater than or equal to p. Okay, and we call this, at least the version we're using here, there are two principal ways to do it. We're going to talk about the Lamuto partitioning. Okay, and next chapter we're going to talk about Hoare's algorithm, which does the same problem. In fact, it starts from Lamuto and does more with it. Okay, so the idea here is that we're going to assume that the first element that we're looking at in our array is going to be p. Okay, we're then going to start comparing to see whether or not we're going to move elements to the right or to the left. Okay, so in this case we have p. Okay, as we move forward in p, we're going to divide things up into those that are less than, those that are greater than, and then some set of which they're unknown. Okay, and finally, when we're done with this, we're going to get p followed by all of those that are less than, all those that are greater than. Okay, all the question marks have been resolved. Okay, and then once we've done that, we're going to move p into the middle. Okay, so that's how that's going to work. So here's the code here for this. Okay, so the input's going to be a subarray. Okay, and then the output's going to be the partition of that and the new position of the pivot. And again, we're assuming here that the pivot is equal to the first element. Okay, and that's kind of how we go through that. Okay, and then there's the quick select, which is a way we're going to partition for a particular one of those the k smallest element. Okay, so that's going to be the k then becomes an input into it. Okay, and we're going to go ahead and do the Lamuto partition. Okay, and then if not, we're going to do this again, basically the quick select again on the smaller subset. Okay, until we figure out how this works here. Okay, so here's an example where they're going to apply the partition-based algorithm to find the median of the list of numbers 4, 1, 10, 8, 7, 12, 9, 2, and 15. In this case, we're looking for just the median, so k is equal to 5. Okay. So again, we start here. Okay. We've got our s and our I as we're moving through. Okay. And we're looking for things that are bigger or smaller, okay, than the one we're, the pivot point that we're looking for. Okay. So that just gives us an example of how this is working. And we're going to keep moving through until we can find our median value there, in which case there's half to the left and half to the right. Okay. And this turns out to be an n-squared algorithm, which from the algorithm, yeah, it doesn't, the quick select is recursive, so it doesn't tell us this other algorithm here. Yeah, it's gonna have a better feel for how that's happening. Okay, so we're doing all the work as we go around each time. Okay, so that's an example of what this is going to look like, this quick select. Okay, we also have the interpolation search. With this problem, you're basically indexing, that you're not just randomly, looking at a particular spot. You're trying to get an idea where the search key is likely to be. So the example they give, if you're looking in the phone book for someone named Baker, you don't start in the middle of the book, right? You start toward the beginning. If you're looking for someone named Zablosky, you look toward the end, okay? And that's the idea, that we're going to divide up our the region we're looking for into subgroups, okay? And there's some mathematical ways we're going to do this to be able to get a better idea, okay? So that's what that one's going to talk about, okay? And then in data structures, I assume you talked about the binary search trees, okay? Those are trees where items to the left are smaller, items to the right are bigger always, okay? So we can use that on a search. And if it's a balanced tree, which it's not always, then we should be able to have a pretty efficient search like the binary search tree, okay? So there's an example of how that would work, okay? The game of NaN, we're not really going to mess with that. I think there's enough in this chapter without getting into that, okay? So you can just skip that part. I think that's it for the chapter, okay? So yeah, so we're just getting some examples here of the decrease by a constant, like the insertion sort, the decrease by a constant factor, like the binary search, and the variable size, like Euclid's, okay? We looked at insertion sort, we looked at the topological sorting of a digraph, either from the source removal or the destination, the last one, and reversing them that way, okay? So, and then we did the binary search, right? And then we did, for the variable size, we talked about the selection problem, we talked about the interpolation problem, interpolation search, and we're going to not cover the game of NaN, okay? So that's chapter 4. Look through that. I'll post the homework tomorrow, most likely, and we'll have our normal meeting on Thursday. And let me know before then if you have any questions.